Hello everyone and welcome to the 14th lecture in the course on solar photovoltaic system design. So today we will look at another aspect of solar cell operation, and which is absorption of light in the solar cell. So to begin with, let's see how light gets absorbed in a solar cell as it passes through the solar cell. So if you see this rectangular block here, that represents a solar cell, and there is some light intensity falling on the top surface of the solar cell given as radiation intensity E1, and alongside there is this couple of axes which show the irradiation intensity on the y axis versus the distance or depth in the solar cell on the x axis. So as you can see here, E1 is the incident radiation at the surface of the solar cell. Now as the radiation penetrates inside the solar cell and it goes deeper and deeper, there is absorption of this light intensity which happens, and hence the light intensity continuously goes on decreasing. And it has been empirically established that this pattern of decay of the light intensity in the solar cell is usually a exponential decay. So in passing through the crystal, the irradiance E sinks continuously due to absorption, and the pattern of absorption is in the form of a decaying exponential. So if having understood this, now we can mathematically formulate the absorption phenomena of light in a solar cell. So the course of the irradiance in the absorbing material can be described by means of a decaying exponential function of this form. E at some depth x from the surface of the solar cell can be given as E1 e to the power minus alpha x, where E1 is the incident radiation on the surface of the solar cell, x is the depth from the surface of the solar cell, and alpha is what we define as the absorption coefficient. So alpha is the absorption coefficient here, x is the depth from the surface, and E1 is the irradiance at x equal to 0, or that means at the top surface of the solar cell. Now this absorption coefficient is a property of a material, and it indicates the ability of the material to absorb radiation, or the absorption ability of the respective material. So what do you expect? Would you like to have a high value of alpha or a low value of alpha? So when I ask my students this question in the class, everyone instinctively they answer that yes, we should have a very high value of alpha because it is the absorption ability of the material. However, there is little more to it. It is not so straightforward, because if you see what will happen if you have a very high value of alpha, it means that the radiation will be absorbed very much in the upper layers of the solar cell. So if you have a solar cell schematic, right in the upper layers, lot of absorption will happen, higher the value of alpha. But if you correlate it with our description of the solar cell and its operation at different depths in the last class and a couple of lectures, we have looked at that. So we remember that the top layer is n plus, and then there is a p base, and then there is a space charge region which is little bit on the n plus side and much more on the p side. And this top layer of the solar cell above the space charge region, that is actually the dead layer. Because of the very heavy doping, any photon which is getting absorbed in that region above the space charge region, that will produce electron hole pair, but there is a very high probability that that electron hole pair will recombine and not contribute to any useful photocurrent. So while absorption coefficient being high is good, but then if it is too high, it will imply that most of the radiation is getting absorbed in the upper layers of the solar cell. So there has to be a trade-off. So therefore, to quantify this particular phenomena, we use a related term to this, which is known as the penetration depth, or XP. And penetration depth describes the depth at which the intensity of radiation has decayed by 1 by E times. So if E1 was the incident radiation intensity at the top of the surface of the solar cell, XP is the depth at which the radiation intensity has become E1 by small e. And we can do the small quick derivation. So at depth XP, my radiation intensity by definition I am saying it is E1 by small e, and this is equal to E1 e to the power minus alpha XP. And if I take cancel out E1 on either side, and we take the ln natural log on either side, so you have ln e to the power minus 1 here, and here you have ln e to the power minus alpha XP. So what we can say is that alpha XP is equal to 1, or in other words your penetration depth XP is 1 by alpha. So, as we just now said that high value of absorption coefficient indicates a higher ability of the solar cell material to absorb radiation, but then your penetration depth will also reduce as the alpha increases. So, if you have a very high value of alpha, the penetration depth will be very small. And interestingly, though we want the maximum absorption to happen in the space charge region, but above the space charge region, the n plus emitter layer, that is the like the dead layer where we do not want the a lot of radiation to be absorbed. So, there is a trade off. We can't just simply say that we go on increasing the alpha, then it will be better for the solar cell. There has to be a trade off. We need to look at it that maximum radiation should be absorbed in the space charge region and not in the top dead layer. So, let us compare different solar cell materials, some of the common or important solar cell materials in terms of their absorption coefficients for light of wavelength 600 nanometer. So, this is important. As we will go ahead about absorption of light, we will see that this absorption phenomena is actually sensitive to the radiation at which wavelength we are talking about. So, at different wavelengths the absorption coefficients will be different, and here this table shows the absorption coefficient for light of wavelength 600 nanometer. The reason being why we are talking about 600 nanometer initially, why not 400, 500, 800 or 1000 nanometer, because the solar spectrum, if you recall one of the initial classes we talked about the nature of the solar spectrum, and we saw that as per Wien's law, sun being a black body emitting radiation at around 5800 Kelvin, the maximum radiation intensity comes around 0.5 micrometer or 500 nanometer. So, that is the spectrum, nature of spectrum just outside the photosphere before the radiation has travelled all the way to the earth. But once the radiation travels to the earth and it passes through the earth's atmosphere, there is lot of different phenomena. We have discussed those in detail. There is absorption, there is reflection, there is scattering, and diffused radiation is being produced. So, a lot of different things happen to the radiation as it passes through the earth's atmosphere. And as a result of that, because different wavelengths of light have different susceptibility to these different atmospheric phenomena like absorption, scattering or reflection. So, due to that, the relative intensity or the spectral intensity of the radiation, solar radiation at different wavelengths, that gets little tweaked or little changed during the passage through the earth's atmosphere. So, on the surface of the earth, the radiation from the sun which is received on the surface of the earth, it has a slightly different spectral characteristic than what was the characteristic outside the earth's atmosphere. So, on the earth's atmosphere, interestingly it has been found that for most of the locations on the earth, under normal atmospheric conditions, the peak solar radiation intensity comes somewhere around 600 nanometer, and that is why you will see when we talk about a lot of these light absorption phenomena, we always consider this particular wavelength as one of the important wavelengths. There are other wavelengths also which are important, but this is usually the de facto used for many of the calculations, because this is where the solar radiation intensity or the spectral intensity of the solar radiation is at its peak on the earth's surface. So, having said that, let us look at the table. So, if you see, there are these 4 different common solar cell materials: crystalline silicon, amorphous silicon, cadmium telluride and gallium arsenide. These 4 materials are given, and then they have their absorption coefficients listed here. Now, interestingly, if you see, as per absorption coefficient, crystalline silicon is the lowest among all these. It has only absorption coefficient of only 4000 per centimeter for a wavelength of 600 nanometer. Highest is gallium arsenide, 47,000 per centimeter, whereas amorphous silicon is the second one, 40,000 per centimeter, cadmium telluride on around 37,000 per centimeter. And we just now looked at the concept of penetration depth, which is nothing but xp is equal to 1 by alpha. And if you do the simple calculation, you just take the reciprocal of the absorption coefficient and you convert it into micrometers. Those are the values given in the last column of this table. You can see, so penetration depth for crystalline silicon is 2.5 micrometer, whereas for amorphous silicon it is only 0.25 micrometer, for cadmium telluride is 0.3 micrometer, and gallium arsenide hardly 0.2 micrometer. So, now what it means is that in gallium arsenide solar cell, if you just go 0.2 micrometer below the surface, then the radiation intensity has already dropped to 1 by E, and 1 by E means it is almost around 37% of incident radiation intensity. That means almost 63% of the radiation intensity is absorbed within the 0.2 micrometer layer from the surface for a gallium arsenide solar cell. On the other hand, for a silicon solar cell, it takes around 2.5 micrometer to absorb roughly 63% of radiation is absorbed in the top 2.5 micrometer from the surface. Now, that should now ring a bell in your mind, because we have been talking about it, that the topmost layer, if we are having emitter, we cannot really have a very thick emitter, and that is the reason why we are heavily doping the emitter N plus and P, because we do not want a lot of loss in the dead layer. We want a very thin dead layer, and then lot of absorption happening in the space charge region is what we want. So that is why we have a very thin dead layer, and the overall N plus emitter is very thin one. So like that. Another important thing, many a times I have seen students confusing with this equation, is that when we write this equation like this, we should always remember in this form, when we are writing Ex equal to E1 e to the power minus alpha x. Now Ex here is the basically the radiation intensity available or remaining at depth x from the surface. Okay. So, this is the radiation intensity which is still available or remaining at depth x. So, if I want to find out the radiation intensity which has been absorbed till depth x, so the intensity absorbed will be nothing but 1 minus E of x, or intensity absorbed will be 1 minus E1 e to the power minus alpha x. So, that is something we should always be careful about. I have seen some students making that mistake, confusing between how much radiation is available and what is absorbed. So, we have to be very clear that this form of equation Ex equal to E1 e to the power minus alpha x only tells me what is the radiation still available or remaining at depth x. So, therefore, if I want to find how much is the radiation absorbed till depth x, then I need to do E absorbed will be 1 minus E1, or you can say basically E1 minus E1 like that, or you can say that it is nothing but E1 1 minus e to the power minus alpha x. That would be the absorbed radiation. So, having said that and looking at these values, now some people might get confused that which one is the best solar cell here, because just if we only look at the absorption coefficient, the first impression says that gallium arsenide might be really good because it is absorbing most of the radiation. It has a very high absorption coefficient, whereas the worst one is crystalline silicon, only 4000 per centimeter, the lowest absorption coefficient, and the other two are very close to gallium arsenide. So, what is your understanding? What is your take on this? What do you feel? Which of these silicon solar cells, or the cadmium telluride solar cells, or the gallium arsenide solar cell, which one would be having a better performance in terms of the output of the solar cell? So, if we just look at the absorption coefficient, we might not be able to answer that correctly, and to give you this overview, you can look at this second table here. So, if you look at the maximum efficiency under lab conditions, what we find is that gallium arsenide is definitely the winner. It has got 29% efficiency under lab conditions. Interestingly, second best is crystalline silicon and monocrystalline silicon, 26%. So, that might be sounding little counterintuitive, because gallium arsenide is having the highest absorption coefficient, that is the coming out as also the highest efficiency, whereas crystalline silicon, which was having the lowest absorption coefficient, that is having the second best efficiency just next to gallium arsenide. Whereas your amorphous silicon and cadmium telluride, they also had your absorption coefficient very close to gallium arsenide, but their overall solar cell efficiency is much lower. What is the reason for that? So, that is why we should not just conclude on one factor. There are several factors. As we go ahead, we will be talking about different factors which influence efficiency. For now, let us consider this second factor given here, which is the band gap. So, absorption coefficient only tells me how good is the solar cell material for absorbing solar radiation. So, that is the information what the absorption coefficient conveys. But then once the radiation is absorbed, what happens to that radiation? So, once the photon is absorbed, only if that photon has energy more than the band gap energy, then it will be able to do the useful work for us, which is lifting the electron from valence band to conduction band. That for that this condition has to be satisfied. If this condition is not satisfied, then the absorbed photon is just heating up the solar cell without doing any useful work, and that is where the band gap comes into picture. So, as you can see, though silicon has a low absorption coefficient, but it has a very low band gap also as compared to the other materials in this range. So, low band gap ensures that out of the total photons which are absorbed, many of those photons or most of those photons have that energy to lift the electron from valence band to conduction band. Whereas on the other hand, amorphous silicon having 10 times better absorption coefficient, but then band gap is also significantly higher. So, though it is absorbing lot of photons, but many of those photons do not have the sufficient energy to raise the electron to the conduction band. So, it is just those absorbed photons are just heating up the solar cell without generating the useful photocurrent. And on the other hand, gallium arsenide is almost in between in that range. If you look at between crystalline silicon and amorphous silicon, gallium arsenide is almost midway. And so, it enjoys both the benefits. It has a very high absorption coefficient and not so high band gap is medium. So, out of all the absorbed photons, a significant number of photons are useful for creating the useful electron hole pairs and the photocurrent, and that is why gallium arsenide is the winner here. But crystalline silicon with its low band gap comes second best. So, just to help you remember this, let me give you an analogy. So, it is not important how many photons you are absorbing, that is not the only criteria, but out of the absorbed photons, how many are actually being able to convert to electron hole pairs, that is also important. So, there is an analogy for this. If you look at the Indian traditional medicine system, so there is we call that as Ayurveda. So, in Ayurveda there is this interesting concept which says that it is not important how much you eat, rather it is important how much you are able to digest. So, if you eat a lot of food, but you are able to digest very less, then your body will not get so much nutrition. So, the same thing is happening here. Gallium arsenide is able to eat a lot of photons, but then it is also able to convert most of those photons to useful electron hole pairs. Crystalline silicon, though it is able to eat so called or absorb lesser number of photons, but then a very high proportion of those photons it is able to convert to useful electron hole pairs due to its low band gap. On the other hand, amorphous silicon, though it is capturing lot of photons, absorbing lot of photons, but due to high band gap, most of those photons are going waste, only few are being converted to the useful electron hole pairs and the photocurrent, and that is what reflects here. Amorphous silicon is actually having the lowest efficiency in all these, if you just look at the efficiency under lab conditions. Crystalline silicon, monocrystalline is second best, multicrystalline is slightly lesser, there is a drop of 3% in terms of efficiency because of the phenomena which we discussed in the last class. If you remember, it was known as the surface recombination. So, multicrystalline silicon has lot of surface boundaries, crystal boundaries, and there is a lot of recombination happening there. Due to that, multicrystalline is having slightly lower efficiency than the monocrystalline silicon. And then in the last column we have the commercially available efficiencies for these different types of panels. Gallium arsenide is having a prohibitively high cost, so it is not used for terrestrial applications, rather it is only used for space applications. So, gallium arsenide is mainly for space applications, whereas out of the others, crystalline silicon, both mono and multi, they are used for terrestrial applications widely. Cadmium telluride is also having some niche applications for terrestrial applications, whereas amorphous silicon has a prohibitively low efficiency, so it is not used practically. So, that is little bit about how to look absorption coefficient in the broader context. So, absorption coefficient is just one factor. Along with that, you have to look at the band gap, and then the usability of the absorbed photons also is important to contribute to the overall efficiency of the solar cell. Now, let us do a quick numerical. So, suppose we want to calculate for wavelength of 600 nanometer for these different materials, crystalline silicon, amorphous silicon, cadmium telluride and gallium arsenide. Two things. First is we want to calculate the intensity of radiation remaining at a depth of 50 micrometer, and second is depth by which 99% of the radiation intensity is absorbed. So, let us try it out. So, as we understand, I will do for a couple of these materials, crystalline silicon and gallium arsenide. For amorphous silicon and cadmium telluride, you can try out on your own on similar lines. So, suppose first I do for crystalline silicon, and we know that for wavelength of for lambda equal to 600 nanometer, the alpha or absorption coefficient of crystalline silicon is 4000 per centimeter. So the radiation intensity still remaining or available at a depth of 50 micrometer, I am calling that as E50. That will be nothing but E1, the incident radiation intensity on top, into e to the power minus alpha x. So minus 4000 into x is 50 micrometer, but because my alpha is in per centimeter, I should convert the depth also into centimeters. So this will be 50 into 10 to the power minus 4 centimeter. And if you solve this out, you will get this as around 2.06 into 10 to the power minus 9 E1. So what you see is that almost close to 0. So by a depth of 50 micrometer, almost complete absorption of this wavelength of 600 nanometer has happened already. I mean, much before that probably, because here it is 10 to the power minus 9. On the other hand, if we look for gallium arsenide, let's do simultaneously the calculation for gallium arsenide. So here we have seen that for lambda equal to 600 nanometers, alpha is 47,000 per centimeter. So here E50 will be E1 e to the power minus 47,000 into 50 into 10 to the power minus 4, and this is very small minuscule figure, 8.725 into 10 to the power minus 103 E1, which is as good as 0 for all practical purposes. So that is similar for both these cases. Now let us try the second problem, second part of this problem, the depth by which 99% of the radiation intensity is absorbed. Okay. So if I am saying that E absorbed is 99%, 0.99 E1, what it means is that E remaining should be only 0.01 E1, and this will be now equal to E1 e to the power minus alpha x, and we have to find the x at which the remaining intensity is 0.01 E1, or only 1% of the initial intensity. And for this, let's we can cancel out E1, take the natural log on both sides. So ln 0.01 is equal to your minus alpha x, and therefore x is equal to minus ln 0.01 divided by alpha. Alpha here is 4000. So you will see this comes out to be, this is 4000 in per centimeter. So the value comes out as 0.00115 centimeter, or in other words we can say 11.5 micrometer. So by a depth of 11.5 micrometer in a silicon solar cell, 99% of the 600 nanometer wavelength radiation has been absorbed. And keep in mind that, as we said, 600 nanometer is where the spectral intensity of the solar radiation is maximum, where you are getting the highest peak intensity of solar radiation. So it takes only 11.5 micrometer to absorb 99% of this wavelength for a silicon solar cell. Same thing let us do for gallium arsenide, and for gallium arsenide also we can say if my E absorbed is 0.99 E1, then my E remaining will be 0.01 E1, and that will be equal to E1 e to the power minus alpha x. And same way I can take natural log on both sides, ln 0.01 is equal to minus alpha x, and x will be equal to minus ln 0.01 divided by the alpha here is 47,000, and you will see this comes out to be only 0.9798 micrometer. So less than 1 micrometer, almost in the top 1 micrometer itself, almost 99% of the 600 nanometer radiation has been absorbed. So in this one I will have to a very thin emitter layer. The emitter layer might be hardly 0.1 micrometer or even lesser than that. So that is a little bit on the absorption. However, as we said that the behavior of the radiation inside the solar cell is different for different wavelengths. So so far we looked at 600 nanometer wavelength, and the reason being that this is the point in the overall spectrum of the sun where the maximum spectral intensity is there on the Earth's surface. But then we are interested in other wavelengths also. So it would be good to see how does the other portion of the spectrum, the other wavelengths, how do they behave inside the solar cell. So the title of the review paper is given here. You can, if you want, you can refer to this paper published by Lee et al. in Journal of Electronic Materials in the year 2022, and it's a review paper. It says the title is Absorption Coefficient of Bulk Third to Fifth Semiconductor Materials, a review on methods, properties and future prospects. So, these authors have done some review on the existing literature in terms of how the absorption coefficient of different wavelengths behaves in silicon and gallium arsenide solar cell materials. And as you can see, there are a lot of different graphs given here. So, all these different graphs are basically by different researchers, and they are very much similar. So, the entire literature, body of literature is in coherence in this aspect, and there is a little bit variation here and there in these graphs, but they are almost very closely related because these are all experimental results. So, sometimes there is some fluctuation, some variation in the observed results, but overall the trend is exactly quite similar. And also another thing, if you observe about these graphs, is that on the x axis you have the wavelength in nanometers, and on the y axis you have the absorption coefficient in per centimeter, and the x axis is a linear axis, whereas your y axis is a logarithmic axis. So, I hope all of you are aware of logarithmic axis and how to read a logarithmic axis. So, in a logarithmic axis, each major axis point is 10 times the previous one. So, like here you have 10 to power 0, then the next major point is 10 to power 1, another major point is 100, then 1000, then 10,000, 1 lakh, 1 million and 1 crore, like that. So, that is how we read the log scale. And now you see, interesting thing is that the absorption coefficient for smaller wavelengths, for the ultraviolet region, it is very high. In the silicon solar cell, if you look at the ultraviolet region, the absorption coefficient is of the order of 1 million per centimeter. Whereas, if you go in the visible region at around 400 nanometer, this value comes down to around 10 to power 5 of that order. At 600 nanometer, where the radiation intensity is peaking on the earth's surface, this value we just now saw is around 4000 per centimeter. Then at the red end of the spectrum, visible spectrum, around 700 nanometer, this value comes down to around 2000 per centimeter, and so on it goes down, and when you are in the infrared region around 1100 nanometer, then this value is down to almost hardly 20 or 30, like that. So, there is a very sharp decay in the absorption coefficient as the wavelength increases. So, that is very interesting because that is little counterintuitive as well. Sometimes I have seen my students, they get little confused, but we have to be very clear about this. So, the radiation, ultraviolet radiation, though it has a very high energy, as we understand, the smaller wavelength has a higher energy content, but still the higher energy content is much more easily absorbed in the silicon solar cell or even gallium arsenide solar cell. Whereas the low intensity radiation, which is the infrared radiation, that is not easily absorbed, that has a low absorption coefficient and that is absorbed much deeper in the solar cell. So, smaller the wavelength, the higher it is absorbed in the, or easily or more earlier it is absorbed in the solar cell. So, the top layers of the solar cell, they will absorb any ultraviolet radiation or any violet or blue end of the spectrum of the radiation. Whereas, as you go deeper and deeper, the red end of the spectrum or the infrared will be absorbed only much deeper in the solar cell. So, that is a common phenomenon. Gallium arsenide, again the values are slightly higher, but pattern is almost similar. So, in the ultraviolet region, again it is of the order of 1 million per centimeter. Visible region, the values are much higher, it is of the order of from 10 to power 5 in that order to up to maybe 20,000 by the red side of the spectrum. And here there is a sharp turn around 850, 870 micrometer. Around that value, still it is around 10 to power 4, and after that there is a sharp decay in the absorption coefficient. So, that is how the absorption coefficient of different wavelengths behaves in some of the common solar cell materials like silicon and gallium arsenide. So, before we end today's class, let us also do quickly one more set of numericals, because we talked about these different wavelengths. Let us look at another value of wavelength. Suppose I want to calculate for a wavelength of 800 nanometer for these two materials, specifically crystalline silicon and gallium arsenide, the depth by which 99% of the radiation intensity is absorbed. So, again let us do similar calculation here. Now, we need to read the values from the graph. So, for crystalline silicon, I am taking lambda is equal to 800 nanometer, and the alpha value I will be reading from the graph. So, if you see, so 800 nanometer here, and this you can read from the graph something like this here, and comes out somewhere around 1000 per centimeter. So, around that value. So, alpha is around 1000 per centimeter. So, as you can see, for 800 nanometer, the absorption coefficient of crystalline silicon is only 1/4 of what it was for 600 nanometer. So, as the wavelength increases, the absorption coefficient drops down. So, again we are saying that your E absorbed has to be 99%, therefore, your E remaining will be only 0.01 fraction, 1% of E1, and this will be equal to E1 e to the power minus alpha x, and we can say ln 0.01 equal to minus alpha x. So, x here would be minus ln 0.01 divided by the alpha now is only 1000, and therefore, you get answer as around 46 micrometer. So, whereas for absorbing the 600 nanometer, for absorbing 99% of the 600 nanometer wavelength, only 11.5 micrometer length or depth was needed. So, as we saw here, for 600 nanometer in crystalline silicon, only 11.5 micrometer depth was needed. On the other hand, for 800 nanometer wavelength, the depth needed is 46 micrometer. And same way for gallium arsenide also we can calculate. We need to read from the graph. If you see, for 800 nanometer wavelength, the value is quite close to around 10 to the power 4 or 10,000. So, somewhere in that vicinity. So, for taking lambda equal to 800 nanometer, my alpha for gallium arsenide is 10,000 per centimeter, and for 99% absorption only 0.01 radiation should remain, 0.01 fraction. So, that is equal to this, and therefore, ln 0.01 equal to minus alpha x, or x is minus ln 0.01 divided by 10,000, and this comes out around 4.61 micrometer. So, again for gallium arsenide you see also again it is more than 4 times, whereas for 600 nanometer wavelength 99% of the radiation was absorbed in less than 1 micrometer, only 0.98 micrometer, but for 800 nanometer it is taking around 4.61 micrometer. So, accordingly, based on the absorption coefficient and based on till what wavelength we want to absorb the radiation, we should design the thickness of the solar cell and also the relative thickness of the n plus emitter and p base. And as we discussed earlier, the relative thickness of n plus emitter and p base will also depend on the doping concentration. So, accordingly we should choose the appropriate doping concentration. And also because we are talking about different wavelengths and silicon and gallium arsenide, also always keep in mind that the limiting factor for the wavelength is the band gap. So, for silicon the band gap is 1.12 electron volt. So, only those photons which have energy such that Sc by lambda is greater than or equal to 1.12 electron volt will be useful photons, and if you solve it out you will see that lambda value less than or equal to 1110 nanometers, and that is exactly around the point where this graph is ending. So, basically if I am considering silicon, I will only design the silicon solar cell that it should be able to absorb up to a maximum of 1100 nanometer. Any wavelength beyond 1100 nanometer, that is useless for silicon, because those wavelengths beyond 1100 nanometer do not have sufficient energy to raise the electron from valence band to conduction band. So, I will design the silicon solar cell only for that particular wavelength till 1100 nanometer. On the other hand, for gallium arsenide, as we just now saw a few slides back, the value of band gap is 1.42 electron volt. So, if you do a similar calculation for gallium arsenide, your Eg is equal to 1.42 electron volt. So, the energy of the photon Sc by lambda should be greater than or equal to 1.42 electron volt, and if you solve it out you will see that your lambda should be less than or equal to around 875 nanometer. And interestingly you see that is around the point where there is this sharp drop in the absorption coefficient of gallium arsenide. So, for gallium arsenide, I will design the cell only in such a way that it should be able to absorb the radiation up to a maximum of 875 nanometer. Anything beyond that I will not be interested, because anyways those photons will not have sufficient energy to raise the electrons to the conduction band. So, that is a little bit of insight on the absorption coefficient, and that gives a little bit of insight to us on how to decide the depth of the solar cell. I want to have the depth of the solar cell such that in the useful spectrum range, where the wavelengths which have the sufficient energy to raise the electron to the conduction band, those wavelengths should be sufficiently absorbed. And we can always do this simple calculation to check what is the depth by which, let us say, 90% or 99% of the useful radiation can be absorbed. So, that is it for today. Thank you for joining us. In the next class, we will be looking at some more aspects of absorption of light in the solar cell. Thank you.